Today we're going to look at some differential equations. So previously we've solved equations of this form. Okay, the derivative of the function is, for example, 0.5x. We can find the original function by simply integrating the derivative. Okay, and we end up with increase the power by 1, divide by that power, plus c. Okay, and since you practiced a few of these, they should be pretty routine by now. Okay. Unfortunately, in reality, not all problems are that simple. Okay, a lot of equations are of the form dA dt equals Ka. So where the derivative is a multiple of the actual function. Okay, that is, the rate of change is proportional to the amount of the substance present. Okay, so we're trying to get some formula for A. You might think, all right, just take dA dt and divide by K. Okay, that's not going to be very helpful because we don't know what dA dt is. Okay, we want some formula for A. And I'm not sure what A is going to be, but I know that dA dt is going to be pretty much the same function. Okay, because see how the slope is some multiple of the original function. So let's have a look at some typical types of functions and see which ones have a derivative that's the same. Let's have a look. So derivative of a constant is 0, no good. Derivative of x functions, no, they're just numbers. If I differentiate a polynomial, I get 1 power less. So that's no good. Sine goes to cos goes to sine, tan goes to sec squared. None of these are any good. We haven't looked at any inverse trig functions. Ooh, let's have a look at this. So in exponential functions, the derivative of an exponential function is the exponential function times a number. Okay, same with base e. So over here, we're expecting to get a equals something with e to the power x in it. Okay, we're going to derive it by first principles, so I'll be able to do it manually, but this is the idea. So hopefully we get something with a e to the power in our solution for a. So I'll start with dA dt equals Ka. Going to do a thing called separation of variables. So this dt, we're going to multiply both sides by dt. Ka times dt. I can't integrate both sides yet because I've still got that a dt over here. If I tried to integrate it, I'd be integrating a with respect to some other variable and be in all sorts of trouble. So I'm going to divide both sides by a. So I get dA on a equals k dt. And now I'll integrate both sides. So the integral of dA on a is the integral of k dt. And now I can have a go at integrating. Remember, integral of dA on a, there's really a 1 here. If you want to imagine that there's a 1 there. Okay, this is the natural log of a. And on the right hand side, integrating some constant, some number with respect to t. So imagine integrating 3 dt would be 3t plus c. So if it's k, it'll just be kt plus c. Okay, now I want to get a by itself. Recall that natural log is log base e. I should be able to convert this now into an index statement. So a equals e to the power kt plus c. Yeah, this plus c is going to be problematic. I'll use the reverse of index laws. Okay, this addition in the powers would have come from two things with base e multiplied by each other with those two powers. Okay, so from here, I'm going to try and find what e to the power c could be. Okay, I know that when t equals 0, the amount is the initial amount. Okay, remember A naught is initial amount or initial value. Okay, so I can sub those values in. A naught equals e to the power k times 0 times e to the c. A naught equals e to the power 0 times e to the power c. And recall that anything raised to the power 0 is 1. Who said 0? Hopefully no one. Okay, so I can rewrite this as A equals e to the power kt times A naught, or write it in the nicer form that we normally see. Okay, so this little step here is explained by that part on the side. So you get out your highlighters, highlight this result coming from here. Yeah, that's the key. So in future problems, you're not going to have to derive this from first principles. You'll just remember that that conversion is possible. All right, so I'll have a go at one of these problems. A bacterial colony is growing at a rate in milligrams per hour equal to 1.6 times the amount in milligrams already present. So let's have a look. So we know that the rate that the amount is changing with respect to time is equal to 0.6 times the amount already present. Okay, we also know, so I've used this piece of information, if there is 500 milligrams at t equals 0, so when t equals 0, a equals 500, I know that, how much will there be at t equals 5? So I'm going to need to find the formula for A, and then I'll sub in t equals 5. Okay, so I know that something of this form, there's not quite enough room, something of this form is going to get converted to A equals A naught e to the power, in this case the k value is 0.6 t. Okay, from here I can substitute in my initial conditions. I'll probably write here that the solution of the differential equation is how I got there. Okay, so sub in t equals 0, a equals 500. 500 equals a naught e to the power 0.6 times 0. Okay, I'll get a naught times e to the power 0. Okay, a naught equals 500. So my model is going to be a equals a naught e to the power 0.6 t. Yeah, I should have defined variables up here as well. Let a be the amount. Let t be the time. There's no units here. Assume minutes. And the time milligrams. Correction. Don't assume minutes. Assume hours, because that's our rate there. And this is our model. Correction. I know what a naught is now. Okay, how much will there be at t equals 5? Okay, so we'll sub in t equals 5 to find a. A equals 500 times e to the power 0.6 times 5, and this will just be a calculator problem from here. And 10,042.76. 77 if you want. So 7 milligrams. Okay, so after 5 hours, there will be 10,042.77 milligrams. Okay, or about 10 grams. Okay, so from here, there's a whole heap of similar problems. Bacterial colonies growing, interest rates compounding continuously. There's probably some decay problems in here as well, tanks leaking at the base, and some sort of challenge problems down the end. Okay, but they're all going to be the same idea. Start with something like something like this, d80t equals some constant times a. Sometimes you might need to make the variables different, like could be dv dt equals kv. Okay, but we know that this will end up as v equals v naught e to the power kt. Yeah, it'll always be that same type of conversion. So now we go add some of those problems, and good luck.